All right, open up your book to section 8-4. We're on page 405 in your book. And the title of this section is The Composition of Ordinates and Harmonic Analysis. So the objective is given two sinusoids form a new graph by adding or multiplying the ordinates. Those are the y-coordinates. We're given a graph formed by adding or multiplying two sinusoids. Find the equations for the two sinusoids. So we'll deal with the first part of this objective today, and we'll deal with the second part in the second half of this section. All right, a couple of terms here to help us out. Since this is titled The Composition of Ordinates that we're going to deal with here for today. Just a couple of terms here. The abscissa is the term that's given to the horizontal coordinate. Usually it's our x value that we're referring to, but it doesn't have to be x. But it's our horizontal component of an ordered pair. And the ordinate is the name that's given to the vertical component, or the vertical coordinate. That is usually the y value, but again, it doesn't have to be y. It could be a different variable name of an ordered pair. So abscissa and ordinate are the name of those two parts that make up a ordered pair when we're talking about coordinates in the Cartesian coordinate system. So when we use the term composition of ordinates, which again is the title of this section, we're talking about the sum or the product of these y values, the ordinates of sinusoids. All right, just to refresh our memory here a little bit about the general sinusoidal equation. You've seen this general sinusoidal equation now for several chapters. It's written as c plus a times the cosine of b times x minus d, or we could write it in terms of sine, y equals c plus a times the sine of b times x minus d. And again, we've talked thoroughly about what the a, b, c, and d all do for us, and how changing sine or cosine affects this, how changing a from being positive to negative, same with b from changing it to positive, negative, or changing d to any multiple that we add on or subtract based on the period of that function. So we've played around with this quite a bit. The problems that you've seen so far, though, the value of c and the value of a, and for that matter, b and d are the same story here, but the values of these four unknowns, a, b, c, and d, have all been constants. It's all been a number. But it doesn't have to be that way. So the question is, well, what happens if we change those from being a number to some equation that might involve an x, a variable? So let's talk about c. If c, which of course is our sinusoidal axis, if c involves a variable, and so instead of just being a number there, if it involves some variable, then that means that your sinusoidal axis is going to vary because of the fact that it involves a variable. So it's not going to be just a horizontal line as our sinusoidal axis, but it's going to have some sort of slope or curve to it, depending on the variable and the equation that we're replacing c with. Likewise, if we do the same thing with a, which of course is our amplitude, if a involves a variable, then that means that the amplitude is going to vary. So your function might not have the same amplitude all the way through. If we're close to the origin, it might have a smaller amplitude than if I'm further away from the origin, in other words. So the amplitude could vary if I make that a variable. So let's graph a couple of functions here just to kind of give us this idea of how involving a variable for the a and the c could change the graph here. So we're going to graph the following functions, and we're also going to graph either the sinusoidal axis or the amplitude for each one. So let's start with this first pair here. We've got the function y equals x plus sine of x. So realize that what you're looking at here is you've got some constant, actually it's not a constant, some quantity, which is x, plus the sinusoid. So this is your c value here. Versus over here on the right, we've got some value that we're multiplying by this sinusoid, so that's in essence the A value from that equation that we have above. That's affecting the amplitude. All right, so let's try this out. Go ahead and grab your calculator. And let's go to our y equals menu. And let's graph the sum first of all. So we've got x plus the sine of x. And you want to be in radian mode. And let's go ahead and graph the sinusoidal axis along with this. So that would be the x. We're thinking about the general equation here, c plus a times the sine of b times x minus d. And you go through and figure out what are the a, b, c, and d there. The c value is that x that's out front. So that's what we're graphing along with this. And probably a standard window here should be fine in radian mode. And there we go. The sinusoid does not oscillate back and forth along the x-axis anymore, but rather it oscillates back and forth around the line y equals x. What happens when we multiply these? So if I multiply those together, x times the sine of x. So again, think of your general equation there, c plus a times the sine of x. That x that's out front now is getting multiplied by that sine of x, so that means that's our amplitude we're talking about. So the amplitude is varying. And again, we'll graph x along with it. I'm going to actually graph both x and the opposite of x because your amplitude could be positive or, the amplitude is always positive, but the a value could be positive or negative. So we'll sketch both of these with it. And when you graph this, again, you can see that the amplitude is varying. And when I'm really close to the origin, the amplitude is really small because I'm multiplying by x. So that's multiplying by a number really close to 0. As I get further and further away from the origin, though, x keeps getting bigger and bigger and bigger. The amplitude keeps getting bigger and bigger and bigger. And you'll notice that those two lines there, y equals x and y equals the opposite of x, are the bounds, the upper and lower bounds for this sinusoid. All right, let's try another one here. Actually, maybe I should grab a picture of that. Actually, I'm not going to worry about a picture of it. We'll just graph these, and you can draw a picture there on your paper if you want to see that. So let's graph two more here. Let's use the square root function, I guess, is the next two. We're going to do a sum and a product here for each of these. So let's do that on our calculator. We've got the square root of x. We'll do the sum first of all. And let's graph the square root of x along with it. Now, the square root of x has a restricted domain here. That is, it's not defined for negative numbers, so it won't make sense really to graph this on the negative domain. So maybe we'll just focus on the positive domain. In fact, let's do that. Let's change our window to go from, say, 0 to 20. And when we graph that, we can see that our square root function there is in red, and we are oscillating back and forth around that. That's exactly what I know about the sinusoidal axis. My sinusoid oscillates back and forth around the sinusoidal axis. What happens when we change this to a product? Again, I'm going to graph not only the positive square root, but I'm going to also sketch the opposite of that. And again, that's because the a value there, we can make it positive or negative. And that determines our upper and lower bounds for this function when we graph it. Again, as you go further from the origin, you can see that the amplitude is getting bigger and bigger and bigger as we go further and further to the right. And it's bounded by that square root function, square root of x. So these are the types of graphs we want to explore. What happens when we modify the amplitude or modify the sinusoidal axis so that they're not just constants? All right, so let's take a look at example 1 there on page 407. The example there says, the figure there, 8,4D, shows the graphs of 3 cosine of theta and sine of 4 theta. And it says, on a copy of this figure, sketch the graph of the sum of those two, y equals 3 cosine of theta plus sine of 4 theta. And then plot the function on your graph, or how can you tell your sketch, how well does your sketch match the actual graph? So we're not going to just immediately plug this into our calculator and see what the sketch is. We're going to try to actually come up with what the sketch must look like, and then we'll double check that with our calculator here in just a minute. All right. So here's what they gave us. We're going to let y1 be 3 cosine of theta. We're going to let y2 be the sine of 4 theta. And we want to graph then y, which is the sum of these two. Y is equal to y1 plus y2 there. That's 3 cosine of theta plus sine of 4 theta. And again, when you look at this and think about this in the general sinusoidal equation form, c plus a times the sine or cosine of b times theta minus d, realize that when I'm adding this is like adding the x or adding the square root of x in the previous examples. Since we're adding this on here, this part right here is acting like our sinusoidal axis. This is kind of acting like our c value. Oops. This is being kind of like the c value there. I would expect to see that my sinusoidal axis here is going to vary when we get done with this. All right, so the first thing we need is a good sketch, and give yourself plenty of space here to draw this, but give yourself a good sketch here of both these functions that they gave us, 3 cosine of theta, which is the cosine function stretched vertically by a factor of 3. So it has a period of 360 degrees still, but it has an amplitude of 3 now. And also graph sine of 4 theta, which is your sine function, but now it's been shrunk horizontally by a dilation factor of 1/4. So its period is going to be 360 over 4. That's 90 degrees is what we're going to see here. All right, so we got ourselves a sketch of these two functions. And now what I'm going to do is go through and come up with a series of points that I can plot on this sketch, and then sketch the graph that goes through those points that I've plotted, and that should be my sketch of the sum of these two. So to do that, we're going to go through a series of steps to help us understand exactly how we come up with these points and what they represent here for us. So I'm going to take you through several steps here to give ourselves a good sketch of this thing. The first thing to note is that the larger period function, which in this case is y1, although it doesn't always have to be y1, so don't just automatically assume that if they say this is y1, that's what we're going to oscillate back and forth around. It's the larger period function, which in this case is the y1. That turns out to be the sinusoidal axis. So again, y1 has a period of 360, y2 we said is a period of 90. That's why we're going to oscillate back and forth around y1, the larger period function. The smaller period function, which in this case is y2, will oscillate around that larger period function. So we're going to oscillate a sinusoid around another sinusoid is what we're going to see here. All right, so let's start out with the zeros of y2. That's the smaller period function. I'm going to use y1 and y2 for the ease here, but realize when I say y2, I'm talking about the smaller period function. And when I say y1, I'm talking about the larger period function. So let's start with the smaller period function, y2, and look at its zeros. If y2 is equal to 0, then when I take and add y1 plus y2, since the y2 there is 0, this guy right here is going to be a 0. y1 plus y2, y1 plus 0 is just going to give me y1. So in other words, anywhere that I see that y2 is a 0, I can plot a point right on function y1. So let's do that. I think I'll plot these in. Let's do this in blue. All right, so look at the smaller period function. So that's this guy right here. It's oscillating every 90 degrees. And anywhere that this is equal to 0, like it is right here, I can just plot a point up there on y1, because when I add this 0 to that y value up there, the sum of those two is just that same point right there. Here's another 0, so I'll plot a point there. And here's another 0, so I'm going to plot a point there. And we'll keep going and plotting all these points. Every time I see a 0 on y2, I'm plotting the corresponding point right there on y1. And there we go. We've got quite a few points plotted. And you might see that we've plotted a number of points right on y2, and that should make sense since we've already said that y2 is going to oscillate back and forth around y1. I should see it crossing that function a bunch of times, which is what that's showing us right there. All right. So that's the zeros of y2. We should also consider the zeros of y1. Anywhere that y1 is equal to 0, then of course when I add y1, which is 0, we're saying, plus y2, you'll end up with just y2. Now, in some cases, we might end up with different zeros here versus y2. And in other cases, we might end up with the same thing, which is the case we've got here. That is, if you look at the zeros of this larger period function, there's a 0 right here, and we've already marked that because that was also a 0 shared by the other function, y2. And likewise, there's another 0 here, but I've already marked that. In some cases, those will already be marked at this point, and in other cases, they might not already be marked. So we're just going and checking to make sure we've got all of those marked, all of the zeros of y1 and all of the zeros of y2. All right. Now let's look at the critical points. Critical points of y2, the critical points of your smaller period function. If a2 is the amplitude of y2, which in our case, the amplitude of that smaller period function is 1, but it doesn't always have to be 1. It could have been 2 or 3 or whatever. In this problem, we're making it equal to 1. But if a sub 2, we're going to call it, for the amplitude of y2, if it's equal to a2, then when we take y1 and add it to a2, then that means, sorry, when I take y1 and add it to y2, since we're at its high point or its low point, that means that I can just simply add on whatever that amplitude is onto y1, and that'll tell me how far above or below y1 I should be sketching this point. So if I consider the critical points of y2, that is where y2 hits its high and its low points, then I can just simply plot those points by adding or subtracting the corresponding amplitude from y1. All right, so let's plot those points. All right, so let's start out with the high points, and then we'll come back and do the low points. I think that's how I'll do it. So it looks like we hit a high point right here, and that's 1 unit above the x-axis. So then I'm going to come up here, and I'm going to mark 1 unit above that y1 curve, which is about right here, as a point that we're going to go through. Here I hit a high point, so I'm going to come down here, and I'm going to mark a point that's 1 unit above. It'll be somewhere about right there. And I got another high point right here, so I'm going to mark 1 unit above. You can kind of measure that roughly about 1 unit. And then here's another point where I hit a high point for y2, so I'm going to mark 1 unit above that, which will be putting me somewhere about right here. And finally, one last one here to mark, so that's 1 unit above is about right there. Again, we're going to be oscillating back and forth around y1, so I should see some points that I plot up above, and I should also see some points that I'm going to plot down below. That's what we're going to do next here. So now let's look at when we hit the lower bounds. Here I hit a lower bound here for y2. So that's a value of -1. So if I take this y value here and I add a -1 to it, in other words, I'm dropping 1 unit below it. It's right here. Here we're at a -1, so measure 1 unit below, and we'll be about right here. We're slightly above the x-axis there. Drop 1 unit below this, so that's going to be about right here. 1 unit below this will be about right here. 1 unit below here is about right here. And keep doing that for all those points. Now you can see we've got quite a few points plotted here. So now we should be able to sketch this graph. I'm going to sketch the graph that goes through those points. Right, maybe I'll sketch this in a different color just so I can still see my points when I get done. But now we're going to try to sketch the curve that goes through those points. Oops, let me do this purple. All right. So carefully, as you do this, sketch it so that you go through the points, and also try to get a nice curve here as we're going through this. Some of these are going to be a little bit easier to sketch than others, but we should be able to sketch kind of what this looks like. So starting here, we're going to come down here and up and down, and then up and down. Looks like we should end up with something that looks kind of like that. And it's okay if we're a little bit off in our sketch here. We're just trying to get a rough sketch of what this looks like. But we've gone through and plotted some points at about the right spot so we can get actually a pretty accurate sketch. Even though it is a rough sketch, it should be relatively accurate. All right, let's go ahead and grab our calculator now and see if that, in fact, is what we get on our calculator. All right, so with our calculator, let's just go to our y equals menu. Let me get rid of these other functions we were playing around with. And let's put in the equation of the function they've given us here, which was 3 cosine of theta. And then we're adding to it sine of 4 theta. And since this is in terms of theta, we're in degrees, so let's switch our mode to degrees. And let's also change our window. In fact, I'm going to just use the window that we were working with there. We went from somewhere around negative 90, I think, to about 450. So we're seeing a little bit more than one full period there. We'll set the scale to 90 degrees, should be fine. And for our y values, I think if we oscillate between around negative 5 and 5, we should be good. So now let's graph that. That looks pretty good. In fact, I would even suggest we graph the sinusoidal axis with it, just so we can see it's oscillating back and forth around that. Graph 3 cosine of x. And look at there. Got ourselves a function that's oscillating back and forth around that sinusoidal axis. So that looks pretty good. What we started with compared to what our calculator gave us, we got a pretty accurate sketch of this thing. All right, a couple things to note here about this. What you should notice here is that when you have the sum of two sinusoids, that results in a function in which the sinusoidal axis will vary. That's what we have there, that we're oscillating back and forth around our sinusoidal axis. And the other thing to notice there is that the sinusoid with the larger period is your sinusoidal axis. Again, that won't always be y1. In this case, it was. Maybe in many of the cases, the problems you're going to look at, that will be the case. But just realize that sometimes it will be y1, sometimes it will be y2. There's nothing special about them naming them y1 and y2 for us. So you got to look at which one is the larger period function. All right, so that was a sum. Let's take a look at example number 2 on the next page, page 408. We're going to use the same two functions. We've got y1 is 3 cosine of theta, and y2 is going to be sine of 4 theta. And this time we're going to graph y1 times y2, or that's 3 cosine of theta times the sine of 4 theta. So we've done a sum. Now we're going to look at a product here. All right, so again, the first thing we need to do is start out with an accurate sketch of these two functions that they've given us. So I'm going to start out with the exact same sketch that I've got here. And before I even start this problem, I should realize that when I think of what this general sinusoidal equation looks like, c plus a times the sine or cosine of b times theta minus d, that I'm multiplying this 3 cosine of theta times that sine. And so that's kind of taking the place of what the amplitude A represents for us. So this looks like it's going to be a case where the amplitude is going to be what varies. All right, so let's go through the same, basically the same steps that we just talked about. There will be a few results that are slightly different, but for the most part, we're going through the exact same steps to understand how we come up with the graph of this function. All right, so the larger period function, which is y1, is the amplitude. That's the first thing to notice. We just talked about that up above there when you think about that general sinusoidal equation. And again, the larger period function in this case is y1, but it's not always y1. But from this point forward, when I refer to y1 and y2, we're talking about y1 being the larger period function, and then the smaller period function, y2, will cycle up to and down to the larger period function. Okay, in other words, it's the amplitude for it. All right, let's start out with the zeros, just like we did before, although I think the zeros here are a little bit easier because when you multiply by 0, you get 0, right? So if I look at the zeros of y2, if y2 is equal to 0, that means that when I take y1 times y2, again, the y2 is 0. Anything times 0 is going to give you a 0. So let's plot those points. Anywhere that anywhere that y2 is 0, that's also going to be a 0 of my graph here. So y2 is the smaller period function. So right here I have a 0, so that's going to be a point on my resulting graph. Another 0 here and here. Go ahead and plot all these points. You'll notice that instead of oscillating back and forth around the larger period function like we saw in the previous one, we're going to be oscillating back and forth around the x-axis. Because the sinusoidal axis in this case, there is no c value out front, it's 0. We're going to oscillate back and forth around 0. All right. Now it could be the case that you've also covered all the zeros for y1, but you should always double check that, so that's why this step is in here. Look at the zeros of y1 now. Anywhere that y1 is equal to 0, because y1 is 0, when I take y1, this guy right here is a 0. When I take y1 and multiply them by y2, of course, I'm going to get a 0 as a result. Now, again, it turns out that we've already considered all of those, but you can double check that on our sketch, that I can see that y1 hits 0 here, and I've already got that marked. And y1 hits 0 there again, and it's already marked. Right? And that's because of the fact that the smaller period function has a period of 90 degrees, which 360 is a multiple of 90. But again, it doesn't always have to end up that way. Depends on the functions you're working with. All right, next step. Next step here is to look at the critical points of y2, just like we did before. Let's call a2 the amplitude of y2, of that smaller period function. In our case, it's 1, but it doesn't have to be 1. So that's why I'm calling it a2. Then when you look at y1 times y2, realize that y2 at its upper bound or lower bound is just equal to this amplitude, whatever the amplitude of that function is. It's either plus or minus that quantity. So we can actually just plot a point that takes y1, whatever that value is, and multiplies it by our amplitude to stretch it either up or down, depending on whether we're looking at the upper bounds or lower bounds of y2. All right, so let's take a look at what that looks like up above. I'm going to deal with the upper bounds first, and then we'll come back and handle the lower bounds. So it looks like we got an upper bound right here first. Realize that that upper bound is a value of 1. So when I multiply this function up here times 1, of course, anything times 1 is itself. So actually, this turns out to be pretty nice because the point is right there on that curve. And here, we'll take this value of 1 and multiply by this y value right here. So we'll end up right there at that y value. And then this value times, which is 1, times that value there is going to give me this number right here. And here, when I multiply those two together, I'll get that y value right there because that's just 1 times this y value. And then finally, I've got a y value of 1, my upper bound there. When I multiply it by that value, I get the number on y2. All right, let's do the same thing with the lower bounds. Now, sometimes having the sketch of the vertical reflection of that larger period function would be nice right now, because then you could actually plot these points right on that curve like we were able to do with the upper bounds, but we can still approximate these pretty good. But right here I have a lower bound, so that's a value of -1. When I take that y value and multiply it by a -1, I'm going to get a negative number somewhere down here. So just realize that you got to drop that down below the x-axis there when I take that positive number and multiply by -1. Same thing here. I've got a lower bound of -1 that I'm multiplying by this y value right here. So when I multiply those two together, I'm going to get a negative number right here. Lower bound right here. Now this lower bound is -1, and this number here is a negative value. So when I take a negative times a negative, that's going to end up giving me a positive. So that's going to be a point somewhere up here. And keep going with this. I've got a negative times a negative, so that's going to be right here. Here I've got a -1 times this value right here, so that's going to drop this down below here to somewhere around here. And there's all of our points. Now, of course, you could keep going with finding more and more points to plot to get a better and better sketch, but I think we got enough points now plotted that we can come up with a pretty accurate sketch of what this thing looks like. So let's do that. That's the next step. Sketch the graph that goes through these points. So now let's sketch our function, and again, try to go through these points, get a nice curve as you go through those points. But this is going to do something like this. It's going to come through here. Oops, I'm not sure why it didn't sketch there. Come up to this point, back down. Here's a little bit tricky, but realize that it's going to just hit the x-axis and kind of bounce back. Here again, when I come hit this x-axis here, it's going to just hit the x-axis and bounce back to go through these points. Okay, there we go. There's our sketch of this function for one period of it, or just a little bit over one period of this function. So let's grab our calculator and see what we end up with, see how close that is. So let's go to our y equals menu, and let's change this to a product. So we'll multiply those two together. And I'm going to go ahead and sketch the upper and lower bound for this. So I'm going to sketch the 3 cosine of x, and I'm also going to sketch the opposite of that. That'll help us see that this kind of gets squeezed in between those two curves there. There we go. That right there is our product. It's the amplitude that's varying as we look at that sketch. In fact, let's grab a snapshot of that. Looks pretty good comparing the two. Definitely as you compare these to make sure you got the right sketch, count up the number of cycles that you see there, especially when you see these points where we're crossing through the x-axis or just bouncing off the x-axis. Make sure your sketch is right there. Looks really good. All right, one last thing here to note here about these examples that we've seen. Notice that when you have a product of two sinusoids, that the result is a function in which the amplitude is varies. That's what we just were dealing with there. The amplitude was changing. And also notice that the sinusoid with the larger period is the amplitude. Sketching it along with the opposite of it, doing the vertical reflection of it, actually is pretty nice to kind of see your resulting curve there get squeezed in between those two parts. All right, that is the end of the first part here of section 8.4.